Hello everyone. So this is another recording for this is for lecture 10. In this lecture we're going to be talking about multiplexing in chapter 8. All right. So so far we talked about communication between two nodes, and we looked at different aspects of this. Encoding, the signal modulation, um, uh, recovery from error detection, and then automatic repeat request. So we looked at all of these aspects. But as you probably know, um, you cannot build a network just by using connections between two pairs or between pairs of nodes, right? Because in that case, the number of links will increase exponentially relative to the number of nodes. So if you have two nodes, you have to have a link, a single link between them. If you have three nodes, you have three links. If you have four nodes, now you will have to have six links, and so on, right? So if I want to explain a little bit what I mean by that, see, let's say we have 5 nodes, and I want to connect all of them using point-to-point links as we studied before. So I need to have a link here, I need to have a link here, 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 and then links between all of these nodes. So if you see a simple, maybe I forgot some of them already, like this one here. So the number of nodes that you need to connect a network like this is given by the general formula n multiplied by n minus 1 divided by 2. N is the number of nodes. So we have 5 nodes, means that we need to have 5 by 4 divided by 2, so that's 10 links, right? And you can see that this will go up exponentially. So we have, at some point, we have to change this approach. So the approach that we're going to talk about today is multiplexing. In multiplexing, we're going to use the same link to connect multiple nodes instead of just one. Right? So we will have a link, and we will have multiple nodes that needs to connect to another multiple nodes here. So to do that, we have to use some form of multiplexing. Oh, my drawing probably not good. Let me see if I can do better. So this is a multiplexer, and this is a demultiplexer, which does the opposite. All right, so the principle here, or the idea, is to use this channel to carry multiple connections at the same time. All right, that's can be possible only if the capacity, the bandwidth available in the channel is much higher than the bandwidth needed for each pair of nodes, right? So let's say, hypothetically, if these nodes here need to talk to the nodes to the right, and each one of them require 1 megabit per second bandwidth, right? So how many nodes we have? 1, 2, 3, 4, 5, 6. Let's say 5, 6, and here we have 6 as well. So in that case, the bandwidth available for the link has to be 6 multiplied by 1 meg per second, so 6 megs per second. Otherwise, this will not be possible, right? So we need capacity in the link that equal or exceeds the capacity needed for each pair of communication. All right, so let's see. Let's continue with our slides. So now multiplexing is one of these ideas that is used widely in today's network. In all kind of networks that we are doing sort of multiplexing, right? We call it different names sometimes, or sometimes it's not clear, but we are doing multiplexing. And all the hardware that we have, switches, routers, they are form of multiplexers and demultiplexers. We call them switches, routers, hubs, whatever, but they are forms of multiplexers. They are taking inputs, multiple inputs, and passing traffic to a single input, or sometimes from multiple inputs to multiple outputs, right? So the principle exists in many forms. Okay, we hinted into this idea before when I said we do modulation so that we shift the bandwidth of the signal into another uh, range of the spectrum, right? So I mentioned that in previous lectures. So actually this is one of the techniques that we use for multiplexing. So the first multiplexing technique uses or splits the bandwidth. So we have a huge bandwidth or large bandwidth available in the link. We chop that bandwidth into small pieces and we allocate each piece of bandwidth to a pair of communicating channels. So hypothetically, let's say here we have 6 channels. So let's say we have the example that I gave earlier. We have 6 megabits bandwidth available in the link. So we chop that into 1 meg, 1 meg, 1 meg smaller channels and allocate each one of these 1 megs to a pair. Right? So that's how we do the what we call frequency division multiplexing, FDM. All right. So the idea is we have here, I'm going to use different colors. So we have here the bandwidth available. And the total bandwidth here is 6 megabits per second. So what we do is split this into 6 pieces. And this we'll call channel 1, channel 2, 3, 4, 5, 6. And we allocate each channel to a pair. So channel 1 will be allocated to pair 1 here, and the corresponding node on the other side. Channel 2 will be corresponding or will be allocated to the second pair, and so on. Okay, to do that, we have to move the bandwidth of the signal to a specific channel. All right. So remember when we talked about modulation, I said each node will generate a sequence of ones and zeros. And that sequence, this is time, right? So in frequency, this would occupy a certain bandwidth. And if you go back to the modulation technique that we talked about, and one of the slides showed that each encoding technique occupies a specific bandwidth. So one of these, it doesn't matter which one in particular, but they all have something similar, which looks like a sync function. And they have certain bandwidth. They occupy certain bandwidth. So this is the left side is the signal in time domain, which represents here voltage or amplitude, and this is time, right? And we have zeros and ones represented by different amplitudes each. And the equivalent in so this is frequency. So the equivalent in a frequency domain is they occupy a certain bandwidth here. All right, but each one of these stations, each one of these nodes or terminals or whatever you call them, right, or PCs, they generate similar similar sequence of zeros and ones. Of course, each one of them will generate different sequence, depends on the data, but they all will occupy similar bandwidth. So if I try to send them all in one channel, they will overlap each other, right? Which is not good because they will cancel each other out or destroy each other. So what we need to do is, if we have, let's say, pair 1, pair 2, pair 3, and 4, and so on, each one of them generates a bandwidth like this. We need to move them so that the first one occupies one bandwidth, one channel. The second one occupies another channel, and the third one occupies a third channel, and fourth one occupies fourth channel, and so on. So they don't overlap in frequency, right? Each one of them occupy one part of the spectrum instead of all occupying the same frequency range. How do we do that? We do that using modulation. So we talked about that before. So if we take the signal and multiply it with, well, let's take any one of those modulation technique, but let's take the simplest one, which is the amplitude shift keying. So in amplitude shift keying, we see that we can take the signal, multiply it with a sinusoid wave with a certain frequency, I call it carrier frequency. What we end up with is a signal where there is 1 and no signal when there is when there is 0, right? So that effectively shifts the spectrum from around 0 here to around FC1. And if I multiply the second channel with a different frequency, FC2, right? So that means that the spectrum is shifted to another frequency, FC2. So each one of these channels will be modulated with a different carrier frequency. So the different carrier frequency is chosen to be in the center of the center of the channel. So FC1 here, FC2 here, FC3 here, and I'll multiply each one of the signals with or modulate each one of these signals with a different central frequency, different carrier frequency. So I will end up with something like this. So I'll take the message, the original binary sequence, and modulate it with what we'll call subcarrier. And then all these signals that result S1, S2, Sn will be added together and sent through the channel, right? Because they occupy different frequencies, they don't destroy each other, right? So you will see here at the bottom that the first channel will occupy certain frequencies, the second channel will occupy a second frequency, and so on. And you notice here, we will visit this topic later, but you notice here that we left a gap in between. We'll call that a guard. So we'll make sure that the frequencies don't overlap each other so they don't destroy each other, right? So that's the idea. In the demultiplexing side, what we will do is try to isolate these. We receive one signal, so we isolate each channel by applying a bandpass filter. Right? So the filter is simply, if you look at it from the frequency perspective, so we have a signal that has multiple it carries multiple bandwidths or multiple frequencies from different stations. So what I do is multiply this with a bandpass filter. The bandpass filter is allocated specifically where I want to isolate the channel. So if I allocate it here, for example, it will result in all the channels disappear except the first one. And if I multiply the input signal here with another bandpass filter, so all the other channels will disappear and I will leave only the second channels, and so on. So this way I can pass the signal that came from the receiver and pass it through multiple filters. Each filter will isolate one channel only and the others disappear. And then I'll apply the demodulator. The demodulator will retrieve the original binary sequence, right? So it will remove the carrier and give me back the ones and zeros. So that's the principles behind frequency division multiplexing. And this technique is widely used. We use it in cellular, wireless, and other technologies. All right. So this one, we talked about the guard, right? The guard band. This one, I have to explain it a little bit because uh, um, it relies on some principles in signal processing, and maybe some of you will have some difficulty understanding this. Luckily, you don't have to understand it very well. I just need to explain what it means to have a lower sideband and upper sideband. So to explain this, um, I'll go back and talk about some principles in the frequency representation of the signal. So each signal, when I speak, for example, my voice translated into electrical signal. So the highs become high voltage, the lows become low voltage. There is certain frequencies for every sound. So if this a signal like this, voice like this, would be terrible, but anyway, so a voice signal has a spectrum. So this is time, right? If I convert it, if I look at the spectrum, if I look at the frequency components, I will see that the frequency components of the voice is somewhere between 300, 200, depends on who you ask or who you talk to, is somewhere between 300 and 3200 hertz. Roughly, now it's never like this, it's never clean, it's always something like looks like this. So unless you have pure sine wave, frequencies usually they are concentrated in power in certain range, and then they die out. The frequencies go in amplitude, they die out as they go on both sides, right? So they're never perfectly square. So some people may estimate that the voice is from 200 to 400 or 4000, something like that. But anyway, the old phone system was designed to carry frequencies between 300 and 3200. Sometimes we assume that it's below that or higher than that. Okay, if you try to, so this is the spectrum of voice. The spectrum of the voice is never positive frequencies only. It's usually has an all spectrums, not just voice. They usually have a positive component and a negative component. Okay? So I'm gonna represent the positive component with this green and the negative with red. And here is where it's a little bit confusing. So what does it mean? Does it mean there are negative frequencies? No, there are no negative frequencies. It's just when we analyze the signal in Fourier transform or other techniques that convert the time domain signal to frequency domain, mathematically there must be positive and negative sides, right? When we modulate, when we take a signal, we modulate it, whether it's analog modulated with analog or digital modulated with analog. What we do, as I said many times before, we are actually shifting the spectrum by the amount of the carrier frequency. So here, let's say the middle here is somewhere, what is the middle between 3000 and 3200? 1600, something like that. All right, so if this is 1600 here, hertz, that may not be correct, but let's assume that. If I modulate this with a frequency, with a carrier that it's 1 meg, right? So the result will be shifting the spectrum from around 0 here to around 1 meg. So everything will be shifted by 1 meg, including the negative side. So what you'll see here is the negative side and the positive side both shifted. And funny enough, actually, these will be flipped on the other side as well. There will be a mirror image. So it's not just every time you move something to the right, you will create an image for it to the left. So Anyway, we're not going to go into details of this. I just want to explain what is the lower side, lower band and upper band. So we'll call this a lower band, and we will call this the upper band. And these are the ones that you see in the slides. Now these represent, when we shift them by modulation, they are duplicates. So it's like we are sending the frequency, the same information, but occupying double the space in the frequency domain. So usually we eliminate one of them, right? So when we send multiple voice channels, we don't need duplicates. So we eliminate one of them and keep only one, right? So that explains this graph. We're taking the original voice and then we do modulation. So when we do modulation, we end up with a lower sideband that's actually not appearing here. It's to the left of this arrow, so we don't see it. But when we modulate, it will be shifted, so we see the lower band and the upper band, right? So, and they occupy same space. I mean, double the space, right? So we don't need duplicates, so we remove one of them, we filter one of them out. So you'll see here that when we have multiple channels, we will have multiple side bands, and we keep only the lower, we don't need the upper one. Okay, so that explains one side. So what is this minus 3 dB, and uh, what is this guard band thing? Okay, so that also requires some explanation. So as I said before, when we take the spectrum of a signal, it's not always nicely like rectangular thing. If it was nice like this, so I can put them, stack them one next to the other, right? So each one of these will be a different channel, and we can put them nice next to each other. But that's actually not possible. Why? Because the channels, the spectrum actually occupies some space. And as I said before, the signal has components that has more power, but then the power in the center here, but then the power or the amplitude of certain frequencies die out as we go away from the center. And these don't just go to the zero here, they sometimes go like low, 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 like for a large, or for a big range, right? So if I want to put two signals next to each other, how to put them next to each other? Should I put them like this? So the black one is one channel and the green one is another. If I put them like this next to each other, then this part will overlap, which means that one channel will overlap another. Overlapping means that some of the signal will scramble and we won't be able to retrieve it correctly on the other side. So we have to separate them. But by how much? Should I separate them like this? All right, there is an overlap here. Should I separate them further away? So by how much I can safely separate them and make sure that whatever overlap happens, it doesn't corrupt both sides. So it turns out that what I need to know is actually where is the power concentrated. And you saw this before when you have a sinusoid with a frequency of 1 hertz, for example, or let's say 1 kilohertz, this is represented by one line in the spectrum, and that's 1 kilohertz. But when I have multiple frequencies, then I may have multiple lines here in the frequency domain, and the bandwidth will be measured like f high minus f low, right? But what if the bandwidth actually goes down almost from infinity to minus infinity? So it's never zero, right? It's never f high minus f low. It dies down slowly, as you see here. In that case, I have to artificially decide where to stop considering the frequency. There is no rule actually to says where I have to decide where the bandwidth, but there is a convention that says let's take the point where the power goes from maximum to half. So if this is maximum power and this is the half power, then I'll say my bandwidth actually is between these 2 points. This is the highest frequency and this is the lowest frequency, and this is my bandwidth, right? And the rest is below half power, so I'm gonna ignore it. And also, as a result, even if there is an overlap between two adjacent channels, the overlap will not be big. So the half point is given as minus 3 dp. Right? So you will see when I do the log, 10 log half, I will get minus 3 dp. All right. So in that case, I can, knowing this fact here, I can make sure that the channels are sitting next to each other. So this is the half, so this is the bandwidth of the second channel. And I can leave some space here, call it the guard band. That depends on the design, right? So I may make it small, I may make it big, but that's what I do. So here you can see that the guard band is between this point and this point. So these are considered the half power point. And you can see here in the example is this band here is given as 10% of the bandwidth. So if the bandwidth is 4 kilohertz, 10% is 400. So I may leave each channel is 4 kilohertz, and the guard is 10% of that. Leave it as a space in between, right? Another technique used for optical communication. So in optical communications, we have light, which is electromagnetic signal as well. I can apply the same principle of wavelet of frequency division multiplexing, but in this case, I use colors. Each color will have a specific wavelength, so I can send different streams of data using a different color or different wavelength. So I'll do the same thing. I'll just call it wavelength division multiplexing, but it's no different in principle. So each channel will occupy different wavelength. Another technique relies on dividing the time instead of the frequency. Right? So instead of taking the bandwidth of the entire channel and dividing it into smaller bandwidths, I'll say taking the time instead and divide it. So let me see. I can simply say, okay, so I have these 6 channels again. Here is my multiplexer. And this is the channel, and this is the demultiplexer. So let's say, how do I divide the time? Let's say I'm going to divide every minute. All right, minute is good. Let's say I divide every minute into exactly 6 slots. So every minute will be divided into 10-second slots. So I have 1, 2, 3, 4, 5. Let's say another one, 6. So that's 10 seconds, 10 seconds, 10 seconds. So I end up with 1 minute. Within this cycle, the first 10 seconds is allocated to the communication between the first pair of nodes. The second slot is allocated between the second pair and the third and so on, right? So the first pair wants to talk, so they put their data here in the first slot. Once the slot is over, when the 10 seconds is over, they stop, right? And they have to wait until the second cycle to be able to send data again. So they will send data only in their time slot. Again, here the bandwidth is, they are free to use the entire bandwidth. So the bandwidth is not divided. What's divided is time. They only have 10 seconds to send, and then they leave, and then another channel have another slot to send, and so on. All right, so, but we need to make this transparent to the node. So then we want the node to be not aware of the channel, not aware of the multiplexer. So the nodes may be designed so that they can talk to each other directly using HDLC, for example, or I may connect them to the multiplexer. So I don't want the node itself to be aware of the multiplexing technique, whether it's frequency division or wavelength division or time division. I don't want it to be aware of that. So how do I make sure that it's transparent? So I will tell the node to send anytime they want, right? Don't worry about the multiplexing. So just send whenever you want. The multiplexer itself has buffers. So when it receives data from the node, it will save it to the buffer allocated for that node. So there is a buffer for node 1, buffer for node 2, and so on. So the multiplexer grabs or receives the data from the node at any order, whatever the node wants to send, it sends. The multiplexer keeps it in the buffer, and the multiplexer saves the data in the buffer until the time slot is available for that node to send, right? So the multiplexer handles this. And this is what we see here. So the message is sent to the buffer, and then the multiplexer, what it does, it goes into the buffer and say, well, is there any data available? Yes, okay, send it. No, move on, right? And keep sending it in particular order. So 10 seconds here, 10 seconds here, 10 seconds here, and so on, or whatever the time is. until the cycle is over, and then goes back again to the first buffer and so on. And we will call I called the cycle, I call this period from the start to the end a cycle. We can call it also a frame. So each frame will include multiple slots. Right? Now, in all of the techniques that we saw, there is one drawback. And that one drawback is that any channel, whether it's a frequency channel or time channel, any channel given is always allocated to that node, whether the node uses it or not. Excuse me. And that's the disadvantage of this kind of technique when we have a fixed allocation. So what if the first pair doesn't want to talk or doesn't have any data left to send? What will happen is the slot will go empty, or the channel that was allocated will be waste bandwidth. There will be no data sent. So that's that's one of the techniques that, or one of the disadvantages of fixed allocation. We will see as we go along through the course that how to avoid that. But anyways, just the opposite on the demultiplexer side, each received slot will be, the data from the first slot will be allocated to us, the first buffer. The data from the second slot will be saved into the second buffer and so on. And then this will go to the other node. So this is the flip side or the opposite side of the multiplexer. The data will be saved into buffers and then they will go to the node. All right, so I hinted to this already. I said the nodes shouldn't be aware of the multiplexer, right? So, and the term that we use is transparent. So the multiplexing technique should be transparent to the nodes. This means that all the things that we studied before, like the window, um, the automatic repeat request, all of this should work fine without being aware of the multiplexer. So the multiplexer takes the data, pass it through time slot or frequency slot, and pass it to the other side. The nodes themselves don't see this. They see it as just a one link, just as if they are talking point to the other side. And that applies to error control as well. So any problem that happened either because of noise or because of the multiplexing itself, it should be handled by the nodes. All right, so here is an example of what I mean. We talked about HDLC frame in the last lecture, and in the frames we have here, each one of these represent one part of the frame. So if the F is the flag field, the A is the address field, C is the control field. It doesn't matter what it is actually, really. It's just the idea here is we have a HDLC frame coming from input 1 going to output 1, and another HDLC frame coming from another input. So what happened is, actually you are looking at it from the right side. So flag, address, control, data, and so on, right? So look at it from right to left. So what the multiplexer do is just take the first byte, which is the flag, and send it, then takes the byte from the other side, which is also a flag, and send it. So it will interleave, take byte from here and then byte from here and so on. So this results in this multiplexed data stream that each byte is coming from a different input. So that actually is just two inputs. If we have 6 or 10 or 20, then we will have F1, F2, F3, F4, so on, and then A1, A2, A3, and so on. Right? Um, it depends on the multiplexing size. So it's not always 8-bit. It could be 20 bits. It could be 15 bits. It could be 100 bits. It depends. But this is just an example that it's nicely, the multiplexing is 8-bit at a time. One of the issues with multiplexing is from the multiplexing side. So the multiplexer takes 8 bits from, or whatever number of bits, from input 1, right? So let's say 8 bits here, and then 8 bits from the second, and then 8 bits from the third, right? And it tries to send them. After a while, it may lose synchronization, right? So it will keep sending stream of bits one after another after another. After a while, it may lose synchronization. So we need to have some mechanism to make sure that the synchronization is maintained. So what we do is we add a one control bit to each frame, right? So in another word, if we take this example again, we'll see that we have one bit sent for each frame. This is for synchronization, right? Then we have a time slot, another time slot, another time slot. So a number of time slots. Each one of them will have certain number of bits. And then in the next cycle, in the next frame, we have a sync frame and then time slots. And this continues. So we have a sync. So these are sync or control bits that are used for synchronization. How do I use these? So let's say the multiplexer inserts a 0 or 1 before each frame. So it starts by putting 0 here, and then this data comes from the stations, and then inserts 1, and then sends data from stations, and then inserts 0, and then sends data from station, and then sends 1, and then so this control bits represent a pattern 0, 1, 0, 1, 0, 1 that continues. So the multiplexer keeps an eye on these control bits. If it always sees that they are 0, 1, 0, 1, 0, 1, means that the multiplexer is still in sync. Multiplexer and the demultiplexers, they are still in sync and everything is right. If for some reason it sees 0, 1, 0, 1 and then 0, 0, right? It means that it lost sync, right? Because it's expecting 0, 1, 0, 1, 0, 1. So it's not receiving that anymore. So there must be a lost sync. In that case, the demultiplexer has to take action. Maybe discards some of the data and starts to go back and try to resync again, right? Now, how it goes back to resync, we're not going to talk about that, but this is the idea, right? Okay, we have seen ideally the idea of each one of these um, stations sending exactly the same number of bits in each slot. But what happens if they don't have the same amount of data to send, right? So what happens um, if this first pair have, let's say each channel represents exactly 10 bits, right? So so each one of these nodes, the first one, second one, third one, send 6 bits in each slot. Sorry, I'm talking about time here, not channels. So let's use a different example. Right, so I'll repeat drawing this using only four time slots. So we have time slots for each pair, right? And then let's say the sync bit or the control bit. So each one of these, let's assume it's a 10 bit. The number itself is not important. Okay, so the first pair sends 10 bit, the second pair sends 10 bit, but the third and fourth pairs, they don't have 10 bits, they have only 6. So what happens? We don't have enough bits to fill the time slot. So in that case, we will rely on something called bit stuffing, right? Or data stuffing, or pulse stuffing actually. So the pulse stuffing comes from the idea that we're converting from analog to digital. Um, the idea is simple. We just fill the gap, fill the remaining bits with fake data, right? That's that's simply it, right? So if I have 10 bits to send, 10 bits to send, and 6 bits only to send, and 6 bits only to send. So what I do is put 6 bits here and then put a little bit of fake data. We'll call that pulse stuffing. Here is an example of how we do that when we are mixing analog sources with digital sources. And we'll see why we need it. So let's take this example where we actually, this is the multiplexer. So this circle, the scan operation represents the multiplexer. Here we have analog signals coming from 2 different sources or 3 different sources. 3 actually. The first one sends 2 kilohertz, right? And we need to sample it to convert it to digital. We need to sample it. We need to sample it at Nyquist rate, which means we need to sample it at 4 samples per second, or 4 kilosamples per second, right? So that results in 4 kilosamples per second. If I multiply that by 4 bits, I end up with 8 um, kilobits per second, right? The second source generates 4 kilohertz of analog signal. If I want to sample it, I have to sample it at 8 kilosamples. Multiply that by 4, we end up with the number of bits per second. and the last one is 2. So how do I handle this? Requires twice as much bandwidth uh, or twice as much data as the other two. So how do I handle this? So let's assume I have here, back to my example, I have 3 inputs and 4 time slots. So this sends 10 bits every frame. This sends 20 bits every frame, and this sends 10 bits every frame. So how do I handle this? Well, we can simply say, this is allocated to station 1, right? And this station 2 is allocated these 2 sides, these 2 slots, and station 3 is allocated this slot here. So we are allocating one station 2 time slots. It doesn't matter if they are adjacent or they are separated. It doesn't really matter, because at the end we are using a buffer here to save the data and a buffer here to collect the data. So it doesn't matter, as long as uh, the same slots are always allocated to the same station. It doesn't matter if they are adjacent or far apart. So this is what we did here in this example. The data is coming from here as analog, and you see the switch. The switch turns into source 1, and then switches to source 2, then switches to source 3, and then switches to source 2 again. So it goes 1, 2, 3, 2, 1, 2, 3, 2. Right? This is similar to going to station 1, station 2, station 3, station 2. Right? So this output, they are sampled, and they are sampled because we have 2 and 4 and 2. So collectively, add them together, they are 8 kilohertz. So we need to sample them all at 16, which is twice 16 samples per kilosamples per second, and then convert them to 4-bit each sample. So if we multiply 16 by 4, we end up with 64 kilobits per second. Right? And this example collects first and samples later. We can simply do the sampling before and conversion before, it doesn't matter, right? So in this example, we take the analog and then sample it. We could also take the analog, sample it, and then send it to the multiplexer. So that represents one input. The bottom here represents another input that comes from digital sources. So notice here that the digital sources come at 7.2 kilobits per second. So each source we have from 4 to 11, each one of them come 7.2, 7.2, 7.2. If I add them together, so how can I add them together? So we have 11 minus 4. So we have 8 inputs. Each input is multiplied by 7.2 kilobits per second. So we have 57.6 kilobits per second. That's not an even number. We want, it doesn't fit a nice time slot. So what we do is put pulse stuffing. So we add data. This is what I mean. We add fake numbers so that the 7.2 becomes 8. Instead of 7.2 kilobits per second becomes 8. So we add 0.8 kilobits per second. So now we have 8 by 8 another 64 kilobits per second, 64 kilobits per second coming from the analog sources and 64 kilobits per second coming from the digital sources. Combine them together, we end up with 128 kilobits per second that's going through the channel, right? So this is the multiplexer, has one input from the analog and 8 inputs from the digital sources. So together we end up with 128 kilobits. And that's what we do for pulse stuffing. So we can do this technique for, we saw here in this example, we can, if one of the channels has double or triple the amount of data that needs to be sent, then we can allocate it more slots. Or we can do the opposite. If this one has 9 bits to send, right? So what we can do is allocate one channel to the first station, another channel to the second, and third channel to the third. And then we use pulse stuffing to make sure that we have exactly 10 bits go here instead of 9, right? So we add fake data. And of course the demultiplexer has to take that out, right? So we have to coordinate this between the two. Okay, so this slide talks about one of the most common um, systems used to carry multiple voice channels. It's called the DS1 system, originally used to carry multiple voice channels, multiplex them and send them in one channel, and then later it was modified to carry data as well. So originally voice was sent analog, and then later was digitized and start to be sent in digital form, right, binary form. So this is one of the techniques that was used to do that. So in this technique, the frame carries 24 slots. Each slot has 8 bits, and that represents one voice sample. And one slot is, or one bit here is left for the framing bit, which is for the synchronization, as we talked about. So if you count 24 multiplied by 8, 192, plus the framing bit, so 193, so that results in 193 bits per frame. Now remember, we have to sample each voice channel at exactly 8 kilobits, 8 kilo samples per second, right? If we do that and we want all the voice channels to be sent and received from the other side without any delay, without anybody noticing, we have to actually send them each, all of the 24 uh, all of the 24 channels have to be sent, plus the framing, have to be sent exactly at 128 microsecond. Why 128 microsecond? Well, take the 1 over 125. I said 128, 125. Okay, so I am seeing it here, I'm reading it incorrectly. So we have to send the entire 24 channels plus the framing bit in exactly 125 microsecond. If you take 1 over 125 microseconds, you end up with 8 kilohertz. And 8 kilohertz is the uh, sampling rate of a voice signal. This system was used later to send data instead of voice, right? So to send data, a little bit of modification uh, made. Um, the data rate to send. So if I take 8 samples per second and I send at 193 bits, so I end up with a data rate of 1.44 megabits per second. As I said before, within I have to send the whole frame in a time where that's equivalent to the time between 2 samples. So that's what is happening here. Um, so to modify the system to make it work for data, instead of sending voice all the time, it was modified so that out of 6 frames, so it's not slots, out of 5 out of 6 frames. So each frame will carry 24 channels, right? But every sixth frame um, modified a little bit. So the sixth frame includes a 7-bit words and a signaling bit. So the channels for the sixth frame, they don't have 8 bits of data. They have only 7 bits, and 1 bit is used for signaling, for other information, right? Other information to communicate between the multiplexers and demultiplexers or between the systems. So they send control information. It turned out that um, that was necessary to send control information between the multiplexers. If this system is used for voice, um, the loss of that single bit, it changes the voice, right? So we're taking a bit out of the information, so it changes, but the change is not noticeable by the ears, right? So even if we use the system to send voice information, the loss is small, that's not noticeable. So in the next few slides, we will have example of or 2 examples of multiplexing in modern technologies. So in North America, I don't know about other parts of the world, but in North America, there's something called um, um, cable modem. So originally, the cabling system or cable system is used to transmit TV channels to houses. So what happened, I'll explain this in a simple graph. So we have a station that collects TV signal from radio waves or from other sources, and then it has fiber that goes to neighborhoods, and the houses subscribe to this service. My houses are not good. Let me try again. Let me see here. So these are houses. Each house will subscribe to this service. So they have, this is fiber, and this is coaxial cable. So it goes from the main fiber line to the house, and then the house we have a TV here. And this was what's called the cable or TV cable or cable TV. So this system sends uh, TV channels, and so the signal itself is divided into multiple channels, and each channel will have a different TV station or different TV network. So you watch different you the on your TV you flip between the channels so to watch different shows, right? The system was later modified to carry also data. So you can subscribe to a cable um, internet, right, instead of cable TV. And you install, instead of a TV, you have a cable modem, and you receive and send data instead of TV channels. So how does the system work? Is usually by taking one of these TV channels, and instead of TV, we're using it for data. I don't know which one, it doesn't matter, but we take some of these channels and use them for data. So this is what we call a cable modem, and it's common in North America. I don't know about other parts of the world. Now, so that's an example of um, um, frequency division multiplexing, because it's originally each channel is allocated to a specific TV channel, and we use that also to send uh, data. The problem with this system, however, is that it works well when you have data coming from the head into the house, right? Because we have, as we see here, we can send data from to all houses. The problem is going back, because they all have the same line, right? So how can you send back data? And internet or network communication is full duplex, bidirectional. It's not just one like TV. Or TV you can send, don't receive anything, you just broadcast. But with data communication, you need to have bidirectional. So to solve this problem, um, we use, or the household or the cable modem uses um, a mechanism where it reserves time slots to send data back. Right? So here, I think this represents, these shaded boxes represent a request by the station to send information, right? So there is a mechanism, we're not going to go into it, but um, instead of the information coming from the house at any time they want, they have to pick a slot. They have to say, okay, I want to send information. So the head end say, okay, you can send it in the next time slot, or in 2 time slots ahead, right? So the household waits, the modem waits until the time allocated comes, and then they can send the information. So this is an example of, we said before that um, if something is allocated, if a channel is allocated to a pair of nodes, that channel will be always there no matter what. So even if the station does not have anything to send, they will still occupy that time anyways. That approach is not very scalable. If I have hundreds, like here, if I have hundreds of nodes, hundreds of households, and they all want to send information, then it's waste of bandwidth and waste of time to give everyone, okay, here's the time slot, and it's going to be allocated to you no matter what. If you want to use it or not, it's going to be allocated to you. That wastes a lot of bandwidth. So instead, we have this system of reservation. If you don't want to send anything, that's great. Don't reserve. If you want to send, ask for reservation. That works, and it worked well for years because people noticed, especially early on in the internet days, that people consume information more than they send, right? So they browse, they receive email, they download files. So the information coming is more, or the inbound is more than the outbound. So this system was designed to have asymmetric transmission. Asymmetric means the data that we are receiving is more than what we send. This approach now it's becoming less common because now you see that I am sitting here uh, sending information, recording videos, um, maybe publishing something on the social media. So there is this notion that we are receiving more data than what we are transmitting is changing. So the techniques have been modified to have more symmetric approach than asymmetric. So anyway, but this is one example of um, frequency division multiplexing and also time division multiplexing. So the frequency division multiplexing is used to allocate some channels to broadcast data. Time division is for sending the information back or reserving reserving some time slots. Okay, so this is an example of how it works. So we have a TV coming. So the cable modem or the cable itself is used for receiving a TV signal as well as data signal. So another very common approach uh, for sending for internet connection is using phone lines. So phone lines were designed initially to send and receive phone signals. And um, this is the line itself has certain frequencies, a certain bandwidth was allocated specifically for the voice. We know that the channel, the voice needs about from 20 hertz to 3200 hertz. So old phone systems were designed to specifically carry these frequencies. Modern phone systems can carry more bandwidth. They have better quality, so they can carry higher bandwidth than just 3200 hertz. So why don't we use the extra bandwidth to carry data? So that created what's called ADSL, and the ADSL system is used to carry data in addition to voice. So when you look at the bandwidth, again, it's an example of frequency division multiplexing where the first part of the bandwidth here is for the old phone system, right? So it carries only voice. But then we have two bands here, or two channels, one for allocated for the upstream traffic. So this is the traffic that goes from the user to the internet. And this is for the downstream, from coming from the internet to the user. And you notice here that the downstream bandwidth has more, or the downstream channel has more bandwidth than the upstream. Again, that based on the idea that what we are receiving is more than what we are sending. We are spending more time maybe watching a video on the internet or reading a website. That's more than what we send. As I said before, all systems, so ADSL is asymmetric digital subscriber line. I hope it's asymmetric, or yeah, that's so you see the new systems, or there are other systems that put X here, so X for A or for other letters. and we have DSL. So other systems have more, either more bandwidth or symmetric instead of asymmetric. So they give equal bandwidth to both upstream and downstream. Right. Another way to implement the same system here and avoid having a limited bandwidth to the upstream is to have one bandwidth for both upstream and downstream. Right? Uh, and we use something called echo cancellation to prevent the overlap. I said if we have two channels overlapping each other, they will disrupt each other and they will overlap each other, confuse each other. To avoid that, we have something called echo cancellation. So echo cancellation can be used. So the basic idea is that you subtract, when you send information, you subtract the signal. The signal can come back to you, right? So it reflects. So because you know what you sent, you can subtract the reflection. You take the reflection and you subtract what you sent. So you get only the downstream information without the overlap of the upstream, right? You don't need to understand more than that in this case, but that actually has an advantage of making the upstream go higher. So if I need more bandwidth, I can take more bandwidth for the upstream instead of being limited to just certain bandwidth, which means we're limited to specific bit rate. Right? Okay, so that ends the this set of slides. Right? See you in the next one, and thank you.